respiration first, and then we'll focus on cellular respiration today. We'll come back to photosynthesis later. Okay. All right, here's the equation. Okay, sunlight, carbon dioxide, water, yielding sugar and oxygen. Okay. All right. What is a function of photosynthesis? What is a goal? Yes.
To get energy from the sun.
Okay. And Joseph?
To put it in the form of glucose and oxygen.
Okay, good. Anything else you wanted to add? All right. So I had us how to use the word convert to convert sunlight energy into organic molecule, organic energy, such as sugar or glucose, using what? Convert sunlight energy into organic molecule using, what do we need? Yes.
Carbon dioxide, sunlight, and water.
We already mentioned sunlight, so using carbon dioxide and water. Okay, so that gives a summary of this, right? This gives a summary of the equation. To convert energy into organic molecule or organic compound using carbon dioxide and water. Okay, so we'll unpack this later. All right, reactants are what enter the reaction. So all of these, okay, CO2, H2O, and you may see sunlight as included in the reactant or not. Okay, same. It doesn't matter whether you include it or not, because this is really like not. This is energy. This is not raw material. This is not organic. This is not like elements, right? So you may see this included as a reactant or not. Okay. Products are glucose and oxygen. Okay. The overall goal is to make sugar. Okay. So that's that. Oxygen is byproduct. In the process of making glucose, it makes oxygen. Okay. In order to make glucose, oxygen just comes along. Okay, so this is called byproduct. All right, where does this happen? Within the cell.
The cell.
Chloroplast.
Chloroplast. Okay, cellular respiration. What is the overall goal of cellular respiration? Okay, Joseph?
To convert glucose and oxygen into energy.
Okay, glucose or organic molecule into usable form of energy called ATP by using, what did you say, Joseph?
Glucose and oxygen.
Okay, using oxygen. Okay, because we're converting glucose by using oxygen. Okay, good. That's it. All right. Okay, this ATP is a usable form of energy. This is like chemical energy. All right. Okay. What's product here is reactant there. What's reactant here is a product there, right? So, glucose, oxygen are reactant. CO2, water, and I guess ATP if you want to include energy or word ATP, that's that. Okay, where does it happen? Mitochondria. Good. Okay, so far so good, alright? Can you connect the word autotroph and heterotroph to here? Again.
Autotrophic organisms use photosynthesis, while heterotrophic organisms use cellular respiration.
Okay. Alright, so So then, do autotrophs perform cellular respiration?
Yes.
Do autotrophs perform cellular respiration?
Yes.
Okay. What do the rest of you think? Do autotrophs perform cellular respiration? Yes. Okay. Whether it's autotroph or heterotroph, they need to make ATP. What drives cellular function is ATP. So all cells require ATP. So whether it's heterotroph or autotroph, whether it's producer or consumer, whatever living thing it is, if it's a cell, right, it requires ATP. So it will make ATP. Now, does it perform cellular respiration to make ATP all the time? That depends, okay? It may perform similar reaction to cellular respiration, or it may not. But they make ATP. Whatever mechanism it uses, it makes ATP. Okay? Because some bacteria, for example, bacteria do not have mitochondria. So if cellular respiration happens in mitochondria and they don't have mitochondria, they use a different mechanism. But the thing is, they make ATP, right? They use different mechanism to make ATP. In other words, all cells make ATP. Cellular respiration is one way, okay? Now, in cellular respiration, oxygen is a must, okay? In order to generate ATP from glucose, oxygen is required, all right? Now, I wrote both of these reactions in one equation, right? One equation. Like you take light, sunlight, carbon dioxide, these three components and put together and we get this and that, okay? Or you take these two and you get these three, all right? However, in reality, if you were to look at this whole process, both of these processes involve series of reactions. So you take something, you do something with it, then the next reaction, the next. Somewhere along, it will require CO2. Then somewhere along, it will use water. Somewhere along there, it will start making glucose. Somewhere along there, it will make oxygen. Same here, all right? So don't think, okay, this is very simple or that it just happens in one reaction. It actually involves series of reactions, okay? This is a summary, the one equation, okay? All right. Today, I'm going to explain cellular respiration. So I'm going to erase this side of the chart.
Wait.
You can watch the video.
And you're gonna put this on the classroom.
Yeah. Anytime I make videos, I post them somewhere.
Thank you.
Okay. Cellular respiration happens in cells that use oxygen. For example, like us, we breathe in. How is that oxygen used in cells to make ATP? Okay, so our cells are constantly making ATP. How? It happens in 3 stages. Okay. Stage 1 is called glycolysis. Stage 2 is called Krebs cycle. Stage 3 is called electron transport chain. ETC. Okay. Another word is called oxidative phosphorylation. Okay. That's mouthful. We'll unpack this word later, but in some cases you will come across this phrase with electron transport chain. So I want to just explain it to you so that you're familiar with it. You don't necessarily have to memorize it, okay? As long as you're able to recognize, okay, this is describing what's happening in ETC, okay? Joseph, if you're not able to see very clearly, feel free to move up.
No, it's just
Okay, all right. Okay, let's draw a mitochondria.
These are the 3 stages.
3 stages of cellular respiration. Okay, imagine that this mitochondria is in my cell, the whiteboard. So the whiteboard is the cell, And here's a mitochondria. What is this space?
Cytoplasm.
Cytoplasm. Okay. When you eat food, it gets digested in your stomach to small pieces and further chemically breaks down into even smaller forms. Okay, eventually the glucose will arrive in the cell. All right, it will enter the cell. So we're going to follow a journey or path of our glucose. Let me draw glucose in just write the carbons, right? CCC, 6 carbons. So the glucose arrives within the cell, and before this enters the mitochondria, glucose is split into 2. Okay, that's the first thing that happens to glucose. It splits into 2 3-carbon molecule, and that's the glycolysis. Okay, the first stage is glucose being split into 2. Okay, split in half. It gets split in half. Glyco means sugar. Lysis means splitting. Okay, so literally, glycolysis means sugar splitting, glucose splitting. Okay, so we've split that. Each one, okay, so both of these will enter the mitochondria and move along the cellular respiration. Okay, now before I move on with the rest, anytime the molecule is breaking down or is being cut in half or is splitting, every time the carbon, anytime the bond is broken between the two C's, it will release electrons. Okay, now what are electrons? Electrons are one of the subatomic particles that make up an atom, right? Proton, neutron, and electron. The electron, negatively charged electrons, are going to be released from this molecule. Now, what does it indicate? What does it mean? Electrons are basically stored in the molecule as form of energy. So earlier, we had listed photosynthesis. Okay, it takes in carbon dioxide to make sugar, C6H12O6. Okay, the carbon from carbon dioxide is fixed into one sugar. To make one sugar, how many carbon dioxide does it need?
6.
6 carbons from 6 carbon dioxide, all right? So the carbon is fixed. In that process, it's storing some electrons, all right? So we're going backwards. Whenever you're breaking this down, it's going to release electrons. And electrons are energy molecules. They're high energy things, all right? Now, the thing about electrons is that they cannot be on their own. They can't just be on its own, just hanging there. It has to be on something. Like in glucose, it's stored in glucose. Or other molecules, in the other molecules, electrons are stored there. But when the bond breaks, those electrons come out, they're released. They are picked up by special transporters or special carriers called NAD. Okay, these are carriers, they're electron carriers.
Is that still glycolysis?
I'm backing up, all right, because we're going to see NAD come up everywhere, okay? So whenever sugar is splitting, it's going to be, NAD is going to pick up electrons, okay? So I'm going to just mark this star there, indicating, okay, those electrons that have been released from here are picked up by our NAD, okay? So let's put a mark there, okay? So every time it splits, we're going to see NAD. Okay, so I will mark it with this. Let's write it. Okay. All right, glucose has been split into 2 3-carbon molecules, and now for each one, this is going to enter mitochondria and continue the rest of this cellular respiration. The next stage is called Krebs cycle. And this is a cycle. So in terms of like what happens in the cycle, we need to draw sort of like a cyclical movement. Okay? So series of reaction, many reactions here. One reaction, something else happens, and okay, so on, so on, so on, and so forth. But it's going around and around and around. Okay? In the cycle, all right, what cycles then is something that is a 4-carbon molecule that exists in the cycle. All right, this 4-carbon molecule just keeps going around and around. Okay, now glucose has been split. The 3-carbon molecule is what starts in the cycle. So let's write CCC there. Okay, the CCC is going to right away break off. All right, split. So 1 carbon is going to detach. It's going to come off.
The first step.
Okay. So that 1 carbon is going to come off or break off. All right. What happens to this C is that this joins with oxygen and becomes CO2. So voila, we have 1 CO2 already here. All right. Here we have CO2. We have 1 right there. Okay, from this C. All right. Then now it's shortened to CC, 2-carbon molecule. The 2-carbon molecule joins with the 4-carbon molecule in the cycle, and so since it's turning this way, let's write how many, basically 4C plus CC. So total there's 6 carbons right now, yeah? Okay, so exists as 6 carbon, it's going around. The next thing happens is that 1 carbon then detaches, okay? This is again then what becomes CO2. So now we have 5 carbon molecule, all right? Then this comes off and this becomes CO2. And the 4C carbon molecule that exists in the cycle is recycled continually, all right? But by now, we have lost both C, all 3 C has been lost as CO2, okay? Now, for each of the 3 carbon molecule, it repeats it twice, right? This one goes through like this one goes through the cycle, all right? So by the time the glucose has completed the Krebs cycle, all the carbon from the glucose has been converted into CO2. Basically, the glucose has been broken off completely. There's no more carbon from that glucose anymore. All right? Now, remember, the end goal of cellular respiration is to make ATP. Okay, we haven't really seen any ATP, haven't we? All right? Okay, what has happened though is in glycolysis, the first step of splitting this into 3-carbon molecule, it has made 2 ATP. Okay? In series of reaction, in 10-step reaction, it makes 2 ATP here. Okay? Now, in Krebs cycle, per cycle, so per 3-carbon molecule, it makes 1 ATP. Okay. Let's write this in green. Okay.
This is
Oh, sorry, 2. Since there's two 3-carbon molecules, it will go through the cycle twice, right? Once for this and once for that. And total, you will have 2, right? Okay. All right. In the next 3rd stage, it will make about 32 ATP. We've only had 4 so far. That means the most of it will be made in the ETC. But by now, by Krebs cycle, the glucose has gone. Okay, it's gone. All right. So where is that source of energy to make 32 ATP? That's our question, right? We don't have any more glucose to make 32. Okay, so what's your guess, Joseph?
Is it those electrons that are flying around?
Exactly. The electrons that are flying around or that have come off from glucose are going to be used in ETC to make the rest. Okay? Now, here was ETC because it broke off, right? It released some electrons. Where else did it break? Where else did it split? Save your question, Akina.
The when the carbons were splitting in the Krebs cycle?
Yeah, whenever this was splitting here and here, it's releasing electrons. All right, so I would draw these asterisk mark there, there, and there. Okay, so it has been broken up completely by the end of Krebs cycle. All right, and all of those electron carriers, NAD, will arrive at ETC to make ATP. All right. Okay, Akina.
Like, I don't know for the Krebs cycle, I'm confused where the 4C.
The 4-carbon molecule is what exists in the cycle that goes around and around. And so the 2-carbon, okay, from the glucose joins with a 4-carbon molecule that exists in the Krebs cycle. And now total, it becomes a 6-carbon molecule.
So that's what exists already.
Yeah, this is what exists in the cycle. All right? Yes.
So it's kind of like a shopping cart for the 3-carbon molecules.
Right. It gives this 4-carbon molecule will join with the new 2-carbon molecule in the next round, and the next round, and next round. Okay? So this is like recycled over and over. Okay? All right. NAD with electrons, okay, when it has picked up electrons, it's called NADH. Okay, actually there's a plus sign. All right, it actually picks up some electrons and hydrogen ions, becoming NADH. All right, there is a cousin, sort of like a cousin molecule, cousin carrier to NAD called FAD. Sorry, I always forget FAD. Okay, and with electron, it's called FADH2. All right. So just notice that this is the transporter, the carrier, with electrons. Okay, and these two are without electrons. All right. Sort of like think of these as shuttle buses with passengers, without passengers. In other words, NAD will pick up electrons, and they're now called NADH.
What's FAD?
Hmm?
What's FAD again?
They're like cousin to NAD. So it's same. What they do is same. They pick up passengers. All right. So this might be like a bus, and this is like a, I don't know, taxi or whatever. Right. Okay. Once they drop off or deliver the electrons, they are now back to NAD or FAD. Right. Okay. So yes.
Wait, so how many of each are there for there to be 12 hydrogens? Like how many of each the NAD and FAD models are?
Okay, so we're going to keep track, all right? They're actually set a number, but I'm not so interested in looking at the number, but I will talk about that. Okay, how many NAD and how many FADs does it produce here? Okay, so all right, let's keep track of the reactants and products. All right, what are the reactants here? Reactants. What started the glycolysis?
Glucose.
Glucose. Product. We have 2 3-carbon molecules, right? The name of these 3-carbon molecule is called pyruvate. Okay, pyruvate. That's the CCC, 3-carbon molecule. Since there's 2, right? Glucose split into half, so there's 2 pyruvate. Okay? And I would say 2 ATP. Okay? And what else? It didn't make CO2, it didn't make anything else. Okay? We could talk about the NAD, but we'll just leave that out of our detail. All right, what about in Krebs cycle? This is a product, 2 ATP. What are the reactants? The each pyruvate, in other words, each pyruvate completes the cycle. Okay, so 2 pyruvate making total of 2 ATP. What else? It produced total of 3 CO2, right? Oh, actually 3 there and 3 there, so total 6, right? For each pyruvate. For each pyruvate it makes 1, 3, and 1 and 3. Okay? Yes?
Does the 4 carbon molecule count as a reactant?
No, we will just keep that out of our detail.
Oh, okay.
Right? I guess you could add more details to our chart, okay? Like you said, we could add that to our, but we will not look at it, okay? All right, now, let's keep track of NADs, okay? Over here, it will have made some NAD. Is it 1 or 2? 2. Okay. So it would have made 2 NAD. Okay, now we'll call it NADH. Alright. For each cycle, here's 1. Okay. Here's 1 more. And here's 1 more. Okay, let's do the math correctly. Actually, there's 1 more somewhere here. Okay, so 1, 2, 3, 4, right? 4, and then 1 more cycle, so that's a total of 8. Okay. Also, let's draw with the green. There is 1 FAD here, so that's 1. So 1 and another cycle, so that's 2 FAD. Okay, 2. Okay. Alright. Okay, that's it. All these electron carriers, FAD and NAD, will arrive at the electron transport chain and they will help make ATP. Okay, so let's take a look at this portion. How is ATP made or recycled? Joseph?
Adenosine diphosphate plus phosphate group.
Good. ADP plus the phosphate. Okay, that's how you recharge ADP into ATP. Okay, so in or on the membrane, all right, on the inner membrane, there is a system, okay, or a set of proteins that are embedded all along the inner membrane. Okay, so this makes one set or one system of electron transport chain. There are lots of these systems in the inner membrane. Okay. Of the system, the last one is called ATP synthase. ATP synthase. And this does exactly this, right? This is an enzyme. Enzyme has a word ending ASE. Okay? If it has word ending OSE, what is it? Carbohydrate, glucose, maltose, fructose, sucrose. Okay, those are sugar. ASE is for enzymes, all right, like maltase, sucrase, catalase, okay, lactase, ASE. ATP synthase. So what does that mean? Synthase. Making, right? It's an enzyme that makes ATP. How does it do that? It adds phosphate to ADP. So this structure right there, that's ATP synthase. It's got 2 parts to it, like structurally. There's a part that acts as a channel. All right? The channel allows the protons to diffuse across the membrane. Okay? So it's diffusion, it's a channel. It's allowing the protons, or this is also called hydrogen ions, H+, protons diffuse from an area of high concentration to an area of low concentration through the channel portion of ATP synthase. Okay. The second structure of ATP synthase is this like rotator. It rotates, a rotor. It's like it moves around. All right, it spins. Okay. The spinning part of ATP synthase adds phosphate to ADP. It's like as it spins, it takes the phosphate and like pushes it to the ADP. All right. So as long as it's going around and around, it will keep making ATP. Okay, so then, what keeps it rotating continuously is the flow of protons through it. Okay, so the flow of protons through the synthase keeps it going, and that will continuously make ATP. All right, then what must happen to keep ATP synthase going? We've mentioned that, it has to have a flow of protons, and then it will just keep making ATP. What must happen to keep the ATP synthase going? Who plays basketball? Okay, if Yuki is ATP synthase, and for her to continuously shoot the basket, she needs to get the necessary materials, whatever the ball and the play, it needs to happen, right? So if she's the ATP synthase having to make ATP continuously, she has to have continuous flow of protons through her, right? So that's the setup. In order for her to keep making ATP, she has to have continuous flow of protons through her. So then what does that mean? Protons are going from this space, so these are all protons, okay? And they're flowing from an area of high concentration to low concentration. So where is it going from where? Out to in. What is the name of those spaces? That was the assignment I asked you to do. Draw and label mitochondria. What's the name of the two spaces?
Inner and outer membrane.
Well, that's the outer membrane. This is the inner membrane. What's the space? Name of the spaces. Anybody got that part?
I forgot. It was like...
Okay, this space between the inner and outer membranes is called intermembrane space with the T, intermembrane space. Not inner membrane space, it's called inter, it's like in between, okay? Intermembrane space. The innermost space is called mitochondrial matrix or just matrix.
No.
Okay? Mitochondrial matrix or matrix. So the protons diffuse from intermembrane space into the matrix. Okay? The flow of protons from there to there keeps ATP synthase going. Okay? Now we get that far, right?
Wait.
Okay, if they keep flowing in, yes.
What was the name of the
Inter.
like the other one?
Matrix. Like the movie Matrix.
What?
The movie Matrix? That's a long time ago, right? Okay.
Is it hard reading?
No.
Never mind.
So watch it when you grow up. I don't know. All right. So in order to have continuous flow of protons from there through there, there's got to be a way or mechanism to maintain a high concentration of protons in the intermembrane space, right? Okay. These proteins that are embedded in the membrane as a chain, okay, these proteins pump. They are proton pumps. They pump protons from where to where? So these are what pump protons. So where is it pumping from? To where?
Into out.
Okay, Joseph?
What she said.
Into out. And specifically, I need you to use the names. It's pumping
The proton.
protons from
Inside.
matrix
Uh,
to the intermembrane space. Okay? It's pumping it from the matrix to the intermembrane space. Okay, from low to high, low concentration to high concentration. So you would imagine, okay, they require ATP to do their job. All right. Now, then how do these proteins know to pump these protons? What's going to signal them to keep pumping is the arrival of electrons at the chain. The arrival of electrons to the chain signals them to pump protons. All right? Now, who's going to bring the electrons? The carriers, these carriers, right? So all of these NADs and FADs that have been made so far will arrive at the inner membrane and arrive at the ETC and literally drop off their electrons. So let's say these red dots are electrons. They have picked up these electrons. Where are the NAD? Okay. They have picked up electrons, and they're going to all arrive at the chain and drop off electrons. Okay. Electrons are happy because they are now on something, right? They're not just on their own, they're on something. They're on protein. Electrons will flow. They will flow, or they will go from one protein to the next, from this protein to the next, from this protein to the next. Okay?
Oh, these
The flow, yeah, they go from pump to pump to pump. Okay? They're sort of going in linear fashion. It's going from here to here to here to here. Okay? Now, the traveling or the flow of electrons from pump to pump signals these pumps to pump proton. Okay? There's lots of P's.
Pump.
Okay? Alright, so we get that far, right? So the maintaining a high concentration of protons here is done by the pump and the electrons. Alright, now when these electrons go from there to there to there and arrive at the final protein there, okay, the next electrons are coming. Okay? So these two electrons, or these electrons that have come to the end of the chain, have to be picked up or accepted by something and remove them out of there. Right? Okay? What picks up the electron is oxygen. Right? Oxygen, the O2 there, oxygen will pick up electrons and remove it out of the chain. Okay? So the key role, okay, oxygen's role is very important. If there were to be no oxygen here, then electron will sit there. Electron will sit here. Electron will sit there. Electron will sit there. NADHs and FADHs will no longer have anywhere to drop it off or deliver. Okay? It will back it up. Or it will back up this whole chain. Okay? If NAD and FADHs are not able to drop off electrons, okay, then when glucose splits or when this happens, there's nothing to pick up electrons. In other words, if you were to remove oxygen here, ETC will back up, will stop. Okay, Krebs cycle will also stop. Okay, so the role of oxygen in our cells is right here. What role does it play? How does it help us make ATP? Is right here. Okay. Now, how does it make water? So O2 here, the oxygen is the O in water. Per oxygen, so I write it in half a O2 because oxygen doesn't exist as a single O. They always exist in O2. So in ratio, this refers to 1O, right? Half a O2 plus two electrons plus 2 hydrogen, okay, in ratio, right? They make up 1 H2O. H2O. 2H, oxygen, and electrons make up 1 H2O. All right? So, that's there. Okay? Yes?
So after the electron gets picked up by the oxygen, then it becomes water.
Right, the oxygen picking up electrons becomes water. Okay? All right. So, let's get rid of that out of our... Right there. Okay. FAD, what is the difference between FAD and NAD is that NADs drop off their electrons at the beginning of the chain, the first protein there. Okay. FAD drops it somewhere along, not at the beginning, but sort of midway. Okay, so if you compare the amount of ATP that NAD is worth versus how many ATP is FAD worth, NAD is slightly a little bit more. It's worth a little bit more. Okay, so by ratio, one NAD is worth about 3 ATP, and one FAD is worth about 2 ATP. Okay, about in ratio. All right, that's because the amount of protons that the system pumps is a little bit more with NAD than FAD, right? Okay, if we do the math, how many NADs are there total? We have 2 here and 8 here, so that's 10. 10 times 3, right? 10 times 3 is 30 ATP. 30 ATP, about. And 2 FADH2, so that's worth 2 each, so that's 4, right? Now, we've made 2 ATP here and 2 ATP there, that's plus 4, right? Now, this math adds up to a total of 38, all right? Now, per glucose, it makes about 36 to 38. Okay, 36 to 38. Now that's approximately, right? Approximately 3, approximately about 2. So, in some readings you might see it as 36, some other readings you might see it as a total of 38. Okay, but with our math, this is what we get, 38. Okay, 2 there, and then 30, 34 in ETC. Okay. Yes?
I probably just missed something here, but wait, why are there 14? Okay, if I didn't do the math wrong, I think there are 14 hydrogens in the reaction.
14.
Because there's 2 in the first NADH, then 8, and then with the FA.
What are you counting?
Hydrogens.
We don't care about hydrogens. There's hydrogen ions all over.
Oh, right.
Yeah. There are hydrogen ions. Good point. There are hydrogen ions all over. But in terms of the number of ATP, that's how we get the 38. Okay. So don't try to count the number of electrons or the number of hydrogen ions, because that's sort of beside the point. All right. But just recognize, okay, to make one water, it requires 2 hydrogen, okay, 1 O, and some electron. All right. Specifically, it's 2 electron, 2 hydrogen ions, and 1 O. All right, but that's okay. Yeah, I think that's it. Actually, that's it about cellular respiration. Okay, it happens in 3 stages, and the role of oxygen is important. Okay, knowing that it makes these electron carriers, okay, and electron carriers are the main players in ETC, okay, and in ETC it makes most of the ATPs there, okay. If you were to remove oxygen, the cellular respiration will stop after glycolysis, because glycolysis does not require oxygen. It will happen regardless of whether the cell has lots of oxygen or not. Glycolysis can happen. So it will make a few ATPs, okay, so that could be enough to power our cells to work to a certain point, but after a while, it will sort of use up all its ATP, and this will not be enough to supply the ATP needs for our cells, okay? All right, I'm gonna stop there. Okay. The word, sorry, one more. The word I use the word break down or break off whenever it's splitting, right? When it's splitting, break off or break down. But the word is called catalyzed or oxidized. Okay, glucose is oxidized into pyruvate. Okay? Or the pyruvate is oxidized into a 2-carbon molecule, then further oxidized into, further oxidized. Okay, so the word oxidized or catalyzed, catalyzed. Okay, yeah. So you could use these two words interchangeably. Okay, the word phosphorylation. The word phosphorylation means adding a phosphate. Okay, adding a phosphate. So that means, okay, at ETC it adds phosphate to ADP. Okay, so that's where the word phosphorylation comes from. Alright? Okay.
Wait, Mrs. Kim, can you post this video on Google Classroom?
Yeah, I will. Sean, can you pause that?
Alright.
Yes, I can.